Hello everybody, my name is Lourdes. I come from Galway, Ireland. And my research is tightly related to the previous talk that Christine gave us. It's about multiple source synchronization at an HbbTV client. The talk is called Multi-Site Client-Side Multi-Source Media Streams Multiplexing for HbbTV. This is the first stop in my research. I'm going to talk briefly about HbbTV, about the prototype I've developed, prototype of the media sync, HbbTV, the model I prototype, and the key points that my module used to synchronize audio and video. Those are TBV, SI, service information, and MPEG-2 BSI, program-specific information tables. MPEG-2 transport streams, which is the media delivery system, and the two solutions have been implemented, and I'm going to talk about the output of the MPEG-2 stream. Well, just so I explain the context of my research. This is strictly an HbbTV diagram. We have an HbbTV receiver where you receive all media possible from both brand or broadcast platforms. So you have available all media, but I wanted to create new services. Especially, I was focused in sports. I wanted to synchronize a TV sport transmission delivered by IPTV channel, which you pay a monthly subscription. But then I wanted to give the client the multiple choice of selecting the audio content of this sports transmission. I mean, this is only, in my point of view, only applies to sports. It will be difficult to say, it doesn't make sense to synchronize a film with another audio. It's always content-related media, right? Why internet radio? Well, just to give more choice to users. And then, the problems it comes with the protocols, the delivery systems, and HbbTV is a perfect platform to provide these new services to clients. This is the HbbTV high level at client side of the standard, and this is where the broadband internet radio delivery will come along. Initially, the TV channel will come from the IPTV as well, and we have is received here. Initially, if we have the broadcast media is delivered here this side, broadband media this side, and here is united with the media player. This media sync model is where my idea of where my model would be based within the whole system. My prototype, which I've developed, is in Java. It's basically, we have a video streamer, delivers an MP2 transfer stream of a football game, and the audio that delivers the same football game match via MP3 file. There is the client receiver. This is a software model where we synchronize the two media files, and at the moment it does not work in real time. It stores the result in a file, and so I'm able to play it and see the result. I'm limited by the hardware of the research. Well, first of all, I must say this is a video streamer. It's developed by Java and is connected to an NTP server. This is the audio streamer, also connected to the NTP server. So this is important in relation to the two different sources, wherever they are, wherever the provider is, are synchronized. We are using the RTP library for delivering the both streams. And then mixing model, there are 4 threads, which the RTP thread for the video, the RTP thread, and the same for the audio. We synchronize it, and there it comes the playout with we can watch with VLC media player. We are using RTP for the audio, which in internet radio is not used normally. We are using it as the first step because it gives us the timing information we need for the synchronizing. And also because in the last part of the research, we want to we will have to work in the clock skew detection to maintain align the video and the audio during the playout. And we want to apply for the radio a patent that my supervisor has about the clock detection skew of audio using RTP protocol. What we'll do later on is, once we have all the sync and everything implemented, the last step will be, instead of using RTP for the audio, we will use Dash or adaptive HbbTV delivery systems, because this gives us the choice of actually the client, when adaptive HbbTV protocol gives us the chance to, the client requests the audio to the server delivers a file, which the client gets information to choose which characteristics the audio file the client needs to play perfectly. So we will use these characteristics. So in the video file, the client selects in the radio the audio file that we need the same characteristics as the video file. Okay. Well, I'm going to talk about the key points of I need to synchronize. The MP2, then transfer streams packet structure, and the tables EBB, SI, and MPEG PSI tables. Here we have the MPEG PSI tables, program associate table, the PNT. In my prototype, these are the only things we're using at the moment. Later on, we're going to use TOT, the ones time related, which are TOT and TDT. And the event information table also will be very useful to know when the match starts. Basically, that's the final tables, all the information that we have added in the final video. Up to here, just I know it's small font, but up to here is one video description, one audio. That's the original video stream, and then we just added an extra audio that will be the new audio from the internet radio, and we added for the future work subtitles channel to display information as well to the video via subtitles, which will be done. Okay, timing information and then MP2 stream, transfer stream. This is the header, the payload, those are the fields. Program here in the rotation field is a program clock references. It's 27 MHz, 42 bits, and the presentation timestamps, the coding timestamps are in the PES header. This is 90 kilohertz. In the videos have PTS, DTS, of course the program clock references, the audios, because it only has presentation timestamps. Okay, so we're going to use mainly the presentation timestamp, the clock of the video, the timing is rolled by the program clock references, and the display time of the audio is commanded by the PTS in every transfer stream packet. Well, the first idea we had, it was audio substitution. What about every incoming MPEG-2 packet, which is audio? We just change the audio to the new audio of the internet radio. That is is much simpler. Is less payload for the software, but it has the drawback that once you select the new internet radio, you cannot go back to the original, and we did not go any further with that approach because we consider that adding the second audio and having the two audios permanently available to user will be much better. So the advantage also that this solution has is we don't have to modify any tables in the DVB tables or MPEG-2 tables. We receive a PES audio, we send it to the output buffer, we read the audio for the MP3 internet radio, we correct the PTS if we need to correct it. So far we don't need to do it, we will do it in the clock skew phase, and we send it to the output buffer. If it's no audio, it is only a video or a table carrying information, it just does nothing, it sends it to then a final video stream. This is the audio addition solution, which involves modifying the DVB tables, which adds a little bit of payload, but gives an added value to clients to just have the two audios constantly to choose. Well, if it's an audio, like before, well, it reads the audio, it stores the audio, but also inserts a new audio, and it follows the structure of the audio packets in the video stream. If it's not an audio, it could be a video file. If it's a video packet, no problem, send to the output. If it's a table, MPT table, we have to modify this to tell the client that there is an extra audio file, an extra audio channel. And one is modified, is sent to the buffer. This is the structure of the MPEG transport stream. On top, we'll see we have interleaved 256 PID identifies the video packet, 257 the original audio, 258 the new audio inserted. So what we do is insert, every time we read one audio packet, we insert the new one with the new audio. So it's interleaved one after the other. We've tried two different approaches, which is we have 16 packets of audio of one PES. One PES is one unit of audio divided in 16 transfer stream packets. So what we do is just, when we have one audio, PES, 16 packets, when it's finished, we insert the new one. Or the other way around. You know, the original and the new, or the new and the original. The results are similar. There's not much difference. But in payload in the software, this solution is easier to implement. The next challenges will be initial synchronization and skew detection and compensation. Initial synchronization is nearly done. It will be presented next month in October in the MediaSync workshop. And basically, we initially synchronize the audio and the video via RTP and RTCP, taking into account that we know when the game is going to start. I forgot to tell you, this was tested by the final of the championships, Barcelona, Manchester United, 2010. We had two video streams from ITV and Sky Sports. So that was the video that we used. We transcoded, so we had it in transfer stream format. And then the MP3 file came from the Catalan radio station. They provide the MP3 file of the whole game. So the final result of the video, we know by also the DVB tables, in the event information table, which event, what time it begins. That game started 8:47, 8:45, that day, that time. This is calculated in epoch time, is all the seconds from 1970, and this is related to the NTP timestamps of the RTP protocol. RTP conveys the timestamps and the relationship of the timestamps with the real time, with the NTP times, NTP time. So I'm not going to talk about the initial sync, but it's already working, and also we take into account the MP3, we insert the MP3 audio packets via measuring the MP3 frames time. We calculate, okay, the MP3 frame is has the size of X bytes, this equivalent to such amount of milliseconds. This is the time we have to insert the audio and then the MP2 and transpose it. Skew detection will be the last area that we have to fix, we have to take into account. We have two challenges there. It will be skew detection in the video, which we plan to use one formula in an ETSI standard, 102034 standard, that relates RTP timestamps with PCR's values within the video. We are working in that formula, still not working. And then we also have to detect clock skew in the audio file. So the client, when it detects clock skew in any of those files, is able to correct it and keep, once the video and the audio is initially synced, is able to keep it synchronized over time. Thank you very much.
Thank you very much for your interesting talk. Would you please translate this Gallic thing?
Thank you very much. Don't ask me to pronounce it.
Right. The first question that I would like to ask is, I understand your approach completely. You've been working on the basis of MP3 files.
Yes.
But if you have streams, audio streams over the internet, so internet radio, there will be a delay in that stream, which will not be predictable because of all of these effects of delay changes in the IP network. Now, synchronizing something which comes over a DVB channel with something with changing delays over the IP network, how are you going to do that?
Well, so far we use RTP because RTP gives us the time. And later on, we plan to use HttP adaptive protocols, and we still don't know how to add timing, how to, yeah.
Any additional questions, Lourdes? If that's not the case, then thank you again.